Hello and welcome to another lecture of this course Mathematics for Economics Part 1. So, as you can see on your screen, what we are doing now is we are doing some tutorials of this course. The purpose of doing the tutorial is to make the students equipped with the skill to handle questions, problem solving skills. So, those are the things that they should develop. So, this is the purpose. Also, the tutorials I think will give the students of a flavor of the review, right. The topics that will be covered in these tutorials will be sort of summary of the different things, different topics that have been covered. Without much ado, let us start the tutorial. So, we start with this first topic, which is the real number systems. So, I have written numbers on top, that is the topic of these questions. So, under each topic I will be covering a number of questions, number of problems that are relevant for that topic. All right. So, that is the strategy that we are adopting in this tutorial. So, this is the question. The questions are all in boldface and the solutions are not in boldface, as you can see here. So, the first question is this: find all x such that a modulus of 3x minus 1 is strictly less than 2. Okay. So, let us try to understand what this question is asking. We have to find out all those x's, all those real values of x's such that this condition holds. So, we start with this condition, what this condition means in simple terms, and then we shall try to see whether we can find the solution. Now, this relation that modulus of 3x minus 1 is strictly less than 2, it implies this, right. So, this is the critical stage of this problem. So, what we are applying here is this property that suppose modulus of x is strictly less than a constant small a. So, this is given to us. What this actually implies is this, that x lies between plus a and minus a. Okay, so, that is what it means. A is any constant, a positive constant. So, if modulus of x is strictly less than a, then that means that whatever be the value of x, it lies in this range minus a to plus a. And you can see the reason for that, right. The reason is that modulus of x less than a means what? That even if x is negative, right, then by modulus we take the positive value of that negative number, right. So, take an example, suppose a is equal to 2, right. Now, modulus of x less than 2, what it means is that even if x is equal to minus 1, right, what is modulus of minus 1? It is equal to plus 1, right. So, this minus 1 will also satisfy this relationship, that modulus of x is strictly less than 2. And of course, if x is plus 1, then also it satisfies that relation, because modulus of plus 1 is equal to 1 and which is less than 2, right. So, as you can see that not only x being less than 2 and greater than or equal to 0 will satisfy this relationship, x being less than 0, but strictly greater than minus 2, that will also satisfy this relationship. In other words, x lying in the range from -2 to +2 will satisfy this relationship, right. So, that is why I am writing this this relation, that if modulus of x is less than small a, where a is a positive number constant, then from that I can straight away write this minus a strictly less than x strictly less than plus a. Okay. So, this is the principle that I am applying here, right, in this particular problem. So, what we are saying is that since we know that modulus of x minus 1 is strictly less than a, therefore, whatever within the modulus symbol, that is 3x minus 1, is strictly less than 2 and strictly more than minus 2. We are actually following this pattern, right, this pattern that is getting replicated here. Okay, now we have to use this relation to get the different values of x which satisfy the given relation. Now, from here what we do is that adding 1 to each of these 3 terms, we can add 1 to this term and this term, and if we do so, then this is what we get. Minus 2 plus 1 is minus 1, 3x minus 1 plus 1 is 3x, and 2 plus 1 is 3, right. So, this is what we are getting. In the end, it is minus 1 strictly less than 3x strictly less than 3. Okay, this is what we have got. In the next step, what we do is that we divide again all these 3 terms by this number 3. Okay. And what is the purpose of doing all these is that we want to get x here in the middle term, right. So, if we divided 3x by 3, then we are going to get x as the middle term, but this first term and the third term will also get divided by 3. Therefore, the first term will become minus 1 divided by 3 and the last term becomes 1. So, this is the final sort of chain that we have got, minus 1 divided by 3 strictly less than x strictly less than 1. Okay, so, this is the actually solution. If x lies between minus 1 divided by 3 and 1, then this given relation, that is modulus of 3x minus 1 less than 2 is valid. Okay. So, that is the solution. Okay, here is the second sort of question. For which value or values of x are the following expressions defined? So, this term defined is important. Okay. And there are 2 separate problems actually. Number 1 is this, 2 divided by x square minus 5x plus 6, that is the first problem, and the second problem is 21 x divided by 4x square plus 4x plus 1. Okay, let us start with the first problem, and as we can see, 2 divided by x square minus 5x plus 6, we can write this expression as 2 divided by x square minus 3x minus 2x plus 6. Actually, what we are trying to do is that we are trying to factorize the denominator. Okay. So, that is the general idea. So, from this actually we get 2 divided by, I am taking x common. So, it will become x multiplied by x minus 3, and from the last two terms I can take minus 2 common. So, within the brackets I am getting x minus 3, and therefore, I can take x minus 3 common. So, if I take x minus 3 common, then the other term will be x minus 2. So, in the end the expression actually becomes 2 divided by x minus 3 multiplied by x minus 2. Now, the point that is important in this problem, the point that we are going to use is that this expression is defined, that is 2 divided by x minus 3 x minus 2 is defined if the denominator is not 0. Okay. So, that is the idea that we are going to use here. If in a fraction the denominator is equal to 0, then that fraction is not defined. Okay. So, that is the basic idea here. Therefore, the denominator cannot be equal to 0. So, that is the property that is being used here. Now, the denominator is x minus 3 multiplied by x minus 2, that cannot be equal to 0, right. Now, when is this expression, that is x minus 3 minus multiplied by x minus 2 is equal to 0? This is equal to 0 if there are two cases when x minus 3 multiplied by x minus 2 can be equal to 0. Either if x is equal to 3, right, in that case this part will become 0, therefore, the product becomes 0. So, that is one case, or x is equal to 2, in that case the second part turns out to be 0, and therefore, the product also turns out to be 0. So, therefore, the expression will become something divided by 0 under two values of x, either x is equal to 2 or x is equal to 3, right. So, that is the answer to the question. For which values of x are the following expressions defined? At least for the first problem, there are two actually values of x for which this expression is not defined, and these two values of x are x is equal to 2 and x is equal to 3. So, that is the answer. Now, we are going to take up the second question, and we are going to use the same tactic, right. Let us see how we can do that. Okay. So, this is the second problem, 21x divided by 4x square plus 4x plus 1, right. So, again we concentrate on the denominator. Okay. So, denominator is 4x square plus 4x plus 1, and now we try to play around with the denominator, try to factorize that, and as we can see that this can be actually easily expressed in the a plus b whole square form. The first term is 4x square, so that is nothing but 2x whole square, right, that will give me 4x square. The second term is 4x, and 4x can be written as 2 multiplied by 2x multiplied by 1, and the last term is 1, 1 is nothing but 1 square. So, as we know, a plus b whole square is what? It is a square plus 2ab plus b square. Just to make sure that people remember their high school mathematics, right. A plus b whole square is equal to a square plus 2ab plus b square, and here so 2x can be thought of as the first term, that is a, and 1 can be thought of as the second term, that is b, and therefore, this denominator can be written as 2x plus 1 whole square. Now, again after we have got this term, then we use the previous property that any expression is not defined if the denominator is 0. So, for this expression to be defined, the denominator cannot be equal to 0. What is the denominator? Denominator is this 2x plus 1 whole square. In other words, 2x plus 1 whole square, this should not be equal to 0. Now, this can be equal to 0 if you have 2x plus 1 is equal to 0, right. So, this is not true, only then you are going to get this. In other words, that is why I have written here, in other words 2x plus 1 should not be equal to 0, right. So, 2x plus 1 equal to 0 will land us in problem, and therefore, I can simplify this a bit. It means x is equal to minus half. Okay. So, that is what I have written here, that if x is equal to minus half, then the denominator becomes 0, and if the denominator becomes 0, then the expression that is given is not defined. Okay. So, this is the answer to the second part. Now, you can see that interestingly, although in both these problems the denominator is a quadratic expression, because there are x squares in both the problems. In the first problem, there are two values of x for which the expression is not defined, whereas in the second problem there is just one value of x, which is minus half, for which the expression in the second part is not defined. Okay. So, that was the answer. Okay. Now, we move off to another topic and take up some problems from that topic. This was mathematical logic. To save time, I have written it just as logic, but it should have been mathematical logic, right. We are not talking about any logic here, but the logic that we can handle with mathematics, we are talking about that sort of logic. So, here is the problem. Is the condition x strictly greater than 2 necessary, sufficient, both necessary and sufficient for the following proposition to be satisfied? What is that proposition? This is the proposition. 3x minus 1 is strictly greater than 8. All right. So, the first thing I think the students should try to do is to, whenever a question is asked, they should devote some time to understand what the question is trying to inquire, right. What is the question asking? So, that should be clarified first before jumping into the solution. Okay. So, what is being asked in this question is that there is a proposition which is given, 3x minus 1 is greater than 8, and in this proposition x is involved. X, as we know, is a variable unknown. Now, the question that is being asked is this proposition to be valid, right. For this proposition to be valid, is this condition x strictly greater than 2 a necessary or a sufficient, or both necessary sufficient, right. Again, to repeat, x is an unknown here. So, x can take any value, right. So, it is possible that for multiple values of x, this given proposition is valid, right. But if we are given this particular condition, then this condition, is it a necessary or sufficient, or both necessary and sufficient for this proposition to be valid. Now, how do we attack this problem? We start with this condition, try to make it a little bit simpler and try to compare this proposition with this condition, right. That will give us a clearer idea as to what is the relationship between this condition and this proposition, right. We have to simplify the proposition. So, that is the line of attack. We start with 3x minus 1 greater than 8 and we add 1 to both sides. So, we shall get 3x strictly greater than 9, and in the next stage we divide both sides by 3. So, we should get x is strictly greater than 3. So, this is what this proposition boils down to. Now, what is the condition that we have been given? The condition is x is strictly greater than 2. Let us now try to understand the relationship between the condition and the proposition, and that will give us the answer to the question. Now, if the condition is sufficient for this proposition, right, then if the condition is satisfied, then the proposition will also be satisfied. Okay. So, let us try to see if this condition x strictly greater than 2 is sufficient, right. Okay. So, if x is strictly greater than 2, it does not always imply that x is strictly greater than 3. Okay. And here is an example. Suppose x is equal to 3, right. If x is equal to 3, then this condition is satisfied because 3 is greater than 2, but x is equal to 3 will not satisfy this proposition. The proposition is saying x is strictly greater than 3, 3 is not greater than 3, right. So, here this is an example where the condition is satisfied, but the proposition is not. And there are obviously infinite number of such examples where the x is such that the condition is satisfied, but the proposition is not being satisfied. So, what we can say is the following, that x is strictly greater than 2 is not sufficient, right. It is not a sufficient condition for x is greater than 3, and x greater than 3, as we know, it is equivalent to saying 3x minus 1 is greater than 8, right. So, that is the conclusion that we are getting, that the condition is not a sufficient condition for this proposition to be valid. Now, the next question is it necessary, right. If x greater than 2 is a necessary condition for 3x minus 1 strictly greater than 8. And here actually the answer is correct, that x strictly greater than 2 is necessary for x strictly greater than 3. And the reason is the following, that remember the definition of a necessary condition, that if this condition is not satisfied, right, if this condition is not satisfied, then the proposition is also not correct. Okay. Now, that is the idea that we are going to apply here. So, if this condition is not satisfied, that means x is not greater than 2. Now, if x is not greater than 2, right, then x cannot be greater than 3 either, right. So, if x is not greater than 2 means what? X could be 1, x could be 0, x could be something negative. Those are the cases where x is not greater than 2. But in all these cases, x is not greater than 3 also. So, that is what I have written here. If x is not greater than 2, it cannot be greater than 3, right, and that is the idea of a necessary condition. Therefore, we conclude the following, that x is strictly greater than 2 is necessary for 3x minus 1 is strictly greater than 8. But remember what I have written here, only necessary, which means it is not sufficient and it is not both necessary and sufficient. It is only necessary. All right. So, this is the way this sort of problems can be tackled in logic. Here is another problem from mathematical logic. So, here is the question: A, B, C are 3 statements and the following theorem is true. What is this theorem? Theorem is this: if A is true and B is not true, then C is true. So, this is a theorem which is given to us, and this theorem is correct, it is a valid theorem. Which of the following statements follow from this theorem? Okay. So, that is the question, and there are 5 options which are given to us. We have to find out which of them actually follow from this theorem. Number 1, if A is true, then C is true. Number 2, if A is not true and B is true, then C is not true. Number 3, if either A is not true or B is true or both, then C is not true. So, this was the third sort of statement. The fourth statement is, if C is not true, then A is not true and B is true. And fifthly, if C is not true, then either A is not true or B is true or both. All right. So, these are the 5 options. We have to find out which of them is correct, which of them is actually follow from this theorem, given theorem. Okay, let us see how we can again solve this problem. Now, the theorem can be written in short form as this: A and not B implies C. A and not B implies C, right. If A is true and B is not true, then C is true. So, that is why I have written it in short form as A and not B implies C. Okay. Now, as we know, this sort of statement is equivalent to this statement, right, that not C implies not A or B. So, try to understand how we are doing it. We are flipping it around, and not, the negative of this statement is not C, implies negative of the first one, that is A was there, that becomes minus, that is not A, and here there was and operative, that becomes or, and not B becomes B, right. So, that is the pattern, and so in the end we are getting not C implies not A or B. Now, this is in terms of symbols. What does it mean in terms of words? This can be expressed in words as, if A is not true, remember there is a wiggle expression here, that means A is not true. If C is not true, then either A is not true or B is true. Now, let us see if this is there in any of the 5 options. What is there? If C is not true, then either A is not true or B is true. Okay, so that is the thing that we have to see whether it is there. And actually, if you inspect all these 5 options, then it is there in number 5. If C is not true, then either A is not true or B is true. Here it is also given as or both, but or both is implied. Whenever or is written, it also means that both of them can be true. Okay. So, the fifth option is the correct option. If C is not true, then either A is not true or B is true. That is the correct option. But is any of the other 4 correct? It can be verified that the other 4 do not follow, right. Let us take 1 or 2 to understand how they are not following from the theorem. For example, suppose you take the first one. If A is true, then C is true. Does it follow? What is this theorem saying? If A is true and B is not true, then C is true. So, this part has been ignored when you are writing this one. So, the first one is not correct, right. Similarly, you can see the other 3 are also not correct. For example, if A is not true and B is true, then C is not true. This does not follow, because if A is not true and B is true, so you are taking actually negative of this and you are taking negative of this, and you are saying then that implies the negative of this. That obviously, that sort of statement obviously does not follow from this theorem. All right. So, the last option, that is the fifth option, is the correct one. The other 4, the first 4 are not following from this theorem. Okay. Here is another problem from mathematical logic. A and B are 2 statements. The following theorem is true. A is true if and only if B is true. Which of the following statements follow from this theorem? Okay. The first option is if A is true, then B is true. Second option is if B is true, then A is true. Third, if A is not true, then B is not true. Fourth, if B is not true, then A is not true. And fifthly, all of the above. Okay, these are the 5 statements. We have to find out which of them is correct. Now, the theorem can be symbolically written as A if and only if B, right. Remember, this is what we have discussed in the lectures, that if there are 2 statements A and B, and the relationship between them is this, that if A then B and if B then A, both of them are correct, then we can write it like this: if A, if and only if B. And if we have something like this, A if and only if B, then actually it means the following: if A is true, then B is true. That is, A is a sufficient condition for B. If A is not true, B is not true. That is, A is a necessary condition for B. At the same time, if B is true, A is true. That is, B is a sufficient condition for A. And lastly, if B is not true, then A is not true, and this basically means B is necessary for A. So, all these 4 statements actually follow from this A if and only if B. We can check each of the first 4 statements and ascertain that each one follows from the given theorem. Hence, only the last option 5 is correct, right. So, you can check if A is true, then B is true, that is A implies B. If B is true, then A is true, that is B implies A. If A is not true, then B is not true, that is A is necessary for B. If B is not true, then A is not true. This, and all of these actually are following from this statement, from this theorem. Therefore, I have to choose the last option, because if I choose 1, then that is just partially correct, because 2, 3, 4 are also true, right. So, fifth is the correct option, that all of the above. Okay, here is another problem from mathematical logic. The relation x square less than 4 is true, number 1, if x is less than 2, number 2, minus 2 is strictly less than x, strictly less than 2, number 3, x is strictly greater than minus 2, and number 4, x is equal to 2. Okay. How to again tackle this problem? It can be ascertained that 1, 3 and 4 are wrong options. 1, 3 and 4 means this one, this one, this one, they are not correct. Why they are not correct? Let us take one example. The first one, let us see, if x is less than 2, right, will it satisfy this? For example, if you take x is equal to minus 3, right, then what is x square? X square is equal to minus 3 square is equal to 9, but 9 is greater than 4. Okay. So, this is not being satisfied. We needed x square to be less than 4. What we are getting is x square is greater than 4, right. So, x being less than 2, it does not mean that x square is less than 4. So, that is why the first one is not correct. The third one is also not correct. X is strictly greater than minus 2. Well, if you say that x is strictly greater than minus 2, x could be let us suppose 3, right, 3 is greater than minus 2. Again, if you take the square of 3, you will get 9, and 9 is greater than 4. Again, that will violate this one. If x is equal to 2, then obviously x square will give you 4. 4 is not less than 4. So, that is why 4 is also, the fourth option is not correct. What about the second option? If x lies between minus 2 and plus 2, then if you take the square of x, right, then that is less than 2 square. And what is 2 square? 2 square is equal to 4. So, that is x square is strictly less than 4, and that is what is given here, x square is strictly less than 4. Therefore, the second option is the correct option, right. What is important here in this problem to note is that suppose you take x is greater than minus 2, right. Now, if x is greater than minus 2, it might mean that x is equal to 0 also, and if x is equal to 0, then this relation will be satisfied, right. But that is for a particular value of x. Yes, if x is greater than minus 2, then for some values of x this relation will be satisfied, but not for all, x which satisfy x greater than minus 2, and that is what is important. We have to check for all values of x which satisfy this condition, right. And if at least for one value of x which satisfy this, but does not satisfy this, then we cannot say that this is a correct option. So, the second option is the correct answer here. Okay. Here is a related problem again from mathematical logic. The relation x square plus x minus 6 is equal to 0 is true if x is equal to 0, if and only if x is equal to 2, if x is equal to minus 3, and lastly if and only if x is equal to minus 3. Notice there is a difference between the third option and the fourth option. The third option is saying if x is equal to minus 3, and the fourth option is saying if and only if x is equal to minus 3. Now, how to again tackle this? We start with this relation x square plus x minus 6 is equal to 0, and we factorize. So, it becomes x square plus 3x minus 2x minus 6, take x common, x plus 3 minus, take 2 common. So, that will give you x plus 3, you take x plus 3 common. So, x minus 2 multiplied by x plus 3 is equal to 0. So, this is an equation, quadratic equation with two roots of 2 and minus 3, right. That basically means that this relation is valid for two values of x, one is 2 and the other is minus 3. Now, check if any of these options is correct. For x is equal to 0, obviously this is not going to be satisfied. If and only if x is equal to 2, no, this is also not correct, because it is true that for x is equal to 2 it is correct, but not only for x is equal to 2, it is also true for x is equal to minus 3. So, that is why second option is not correct. The third option is correct. If x is equal to minus 3, then obviously we know minus 3 is a root of the quadratic equation. So, therefore, this is correct. And the problem with the fourth option is that yes, for x is equal to minus 3 the relation is correct, but it is wrong to say that it is correct only for x is equal to minus 3, right. So, therefore, only the third option is the correct option. Okay, now we move to another topic which is sets and set operations. So, we start with the first problem here. Suppose 3 sets are given. First set is A has 4 elements 1, 2, 3 and 4, and then we have set B has 3 elements 2, 3 and 4, and then you have the third set C which has 3 elements 1, 5 and 6. Okay, so, these 3 sets are given to us. We have to answer 4 questions. Show that A union B is equal to A. Can we say anything about the relation between set A and B from the result? Okay, what result? The result that we have given here, that is A union B is equal to A. The second question is what is B intersection C? The third is what is A union B minus A intersection B, and the fourth one is verify that A intersection B union C is equal to A intersection B union A intersection C. Okay. So, let us start with the first one. A is known to us, B is known to us. So, we can find out what is A union B. So, A union B is equal to this set, that is A 1 2 3 4 and B 2 3 4. The union of these two sets will consist of those elements which are there either set A or set B. So, it will be 1 2 3 and 4, and this is nothing but set A, right. So, that is what we were supposed to prove, that A union B is equal to A. Now, what does it mean? Can we say anything about the relation between set A and B from this result? This actually means that B is a subset of A, right. When you are taking the union of two sets, if the union turns out to be one of those sets, that means that the other set does not have any element which is not there in the other set, right. So, that basically means that the first set is a subset, right. Let me repeat that once again. If we are taking two sets, right, A and B, and we are taking the union of them, and the union turns out to be set A, right, then that means that in set B there is no element which is not there in set A also, right, and that basically means that B is a subset of A. It is not necessary that it is a proper subset, but in general, in that case B is a subset of A. And actually this is confirmed by inspecting the sets also. If you look at set A and set B, then each element of B is also an element of A, right, and that basically makes B a subset of A. The second problem is what is B intersection C? Okay, what is B? B is 2 3 4 and intersection C 1 5 6. Now, in intersection sets we take elements which are common to the sets. Now, as we can see that between B and C there are no common elements. Okay. So, therefore, the intersection set is a null set. The third is this, that we have to find out A union B, that is within the brackets, and this backward slash, right, this symbol basically it denotes minus. So, backward slash within the brackets A intersection B. Okay. So, we expand this, and that is what we are going to get. So, this is A 1 2 3 4 union B, what is B 2 3 4, and then you have this symbol, and then within the brackets again 1 2 3 4 the first set, and intersection 2 3 4 the second set B. Okay, now, if we take the union of 1 2 3 4 and 2 3 4, you get 1 2 3 4, and if you take the intersection of 1 2 3 4 and 2 3 4, what are the common elements? They are just 2 3 and 4. So, this is what we are getting, 1 2 3 4 minus 2 3 4. Minus means we have to take out those elements in the first set which are there in the second set as well. Here 2, 3, 4 are there in the second set. So, we take them away and we get only 1, right. So, this is the answer. And last problem, the fourth problem was verify A intersection within the brackets B union C is equal to within the brackets A intersection B union A intersection C. So, we start with the LHS, that is the left hand side. A intersection B union C. A is known to us, it is 1, 2, 3, 4, and then intersection B 2, 3, 4 and union C, that is 1, 5, 6. And then in the next step A remains as it is, we take the union of 2, 3, 4 and 1, 5, 6, and that becomes 1, 2, 3, 4, 5, 6, right. And if we take the intersection of these two sets, that is we are taking the common elements from this set, and this is nothing but 1, 2, 3, 4. This was the LHS, the left hand side. What about the right hand side? Right hand side was this, within the brackets A intersection B, then union within the brackets A intersection C. All right. So, A intersection B means this 1, 2, 3, 4 intersection 2, 3, 4, and union of A intersection C, that is 1, 2, 3, 4 intersection 1, 5, 6. So, from the first term we are going to get 2, 3, 4. So, 2, 3, 4 are common, and from the second we are going to get only 1, right, because this only one element which is common to both these sets. So, 2, 3, 4 union 1, and that will give us 1, 2, 3, 4, and you can see this is the set that we got from the left hand side as well. Hence, we have verified. Okay. This is again a problem from the sets. Which of the following is true? If a statement is false, show a counter example. A minus B is equal to B minus A. Whether it is false or true, that we have to say. If we think it is a false statement, then we have to show a counter example where this statement is not valid. Okay. A minus B is equal to B minus A. Let us see how it is false. We take A to be 1, 2, 3 and B to be 2, 3, right. So, what is A minus B? A minus B means we take out those elements of A which are there in B also. So, this will only leave us with one element, that is 1, and B minus A, if we take B which is 2, 3, from that if we take elements of A, that is 1, 2, 3, we can see that all the elements of B are there in A also. So, there is no element in B minus A. So, it is a null set, and as you can see these two are not equal. A minus B is not equal to B minus A. So, that is why the statement was not correct. The second problem is this: A is a subset of B if and only if A intersection B is equal to A, whether this is correct or incorrect. All right. Our answer is it is correct, it is true. Okay. What is the reason why it is true? It is not being asked that we have to show the reason anyway, but we are trying to clarify why we think that this is correct. Now, when we say that A is a subset of B, it means that each element of A is also an element of B, right. That is the definition of a subset. In this case, A intersection B consists of elements of A, right. So, if we take one to be subset of the other and if we take the intersection set becomes the subset. On the other hand, A intersection B is equal to A implies that each element of A is also an element of B. Okay. So, that was the right hand side, A intersection B is equal to A. So, if this is true, then what does it mean? It means each element of A is also an element of B. Okay. So, that basically means that A is a subset of B. Okay. So, that is why from this is implied and from this is implied. Okay. So, that is why we are saying that the second statement is correct. The third, what is this third saying? A union B is equal to A union C implies B is equal to C. And our answer to this is that it is a false statement. And if it is a false statement as per our claim, then we have to give an example, and here is the example. So, we have taken A to be this set 1, 2, 3, B to be 2, 3 and C to be 1 and 2. Now, let us suppose these are the 3 sets, then if we can show that this is not correct. Okay. In this case, what is A union B? A union B will be 1, 2, 3, right. And what is A union C? It is also 1, 2, 3, both are equal, right. So, the left hand side is satisfied in this case, but obviously B is not equal to C in this case. B is the set 2, 3 and C is the set 1, 2, obviously they are not equal. So, we have constructed one example where even if this is correct, the implied part, the putative implied part is not following. Okay. So, that is why this third statement is not correct. Okay, here is another problem from set theory. In a class, 20 students like economics, 15 like both economics and mathematics, 30 like either economics or mathematics. How many like mathematics? Okay, so, that is the question. Here let us suppose that A is the set of students who like economics and B is the set of students who like mathematics. What we know? We know the number of elements of A is 20, right. A is the set of students who like economics, that is 20. Number of elements in A union B, that is the students who like either economics or mathematics, that is given by 30. And the number of elements in A intersection B, that is the students who like both economics and mathematics, that number is 15. Okay. And this is what we know, this is a theorem that we are going to use here, that n of A union B is equal to n A plus n B minus n of A intersection B. What is n? N x means the number of elements in the set of x. Okay. So, this is a sort of new notation that is being introduced here. If x is any set, then n x it denotes a number, that number is the number of elements in that set x. So, if that is how n is defined, then this theorem follows that n of A union B is equal to n of A plus n of B minus n of A intersection B, right. And from here we can actually manipulate it a bit, and we shall get this relation that n of B is equal to n of A union B plus n of A intersection B minus n of A. Okay. That will actually solve our problem if we use this relation, because we know A intersection B is 30. Students who like either economics or mathematics, plus 15 students who like both economics and mathematics, minus 20 the students who like economics. So, 30 plus 15 minus 20, that will give me 25. So, that is the answer. The number of students who like mathematics is 25. Okay. That is more or less about set theory, right. We talked about actually 3 topics so far. We started with numbers, right, and real number system. Then we talked about mathematical logic, and finally we talked about set operations. Those are the 3 topics that we have covered. Now let us move ahead a bit and start talking about what is known as differentiation. This was, I think, somewhere down the line in our course topics. So, differentiation, derivatives, that is what this topic is about. So, here are some practical problems. First, these are the 3 problems that we are given. Find the first derivative of number 1 x log x, log natural x in this case. Secondly, x plus 1 divided by x minus 1, and third x square minus 1 divided by x square plus 1. So, we have to find this in the first problem, d dx of x log natural x. Okay, now, what we do is that we take the help of product rule. Remember what was product rule? So, you have d dx of u v, right. U and v both are functions of x. And then what we do is that we take the first function, let us say u, right, and then we take the derivative of the second function, plus you take the second function, multiply that with the derivative of the first function. So, that was the product rule, just in case you remember, and that is the thing that we have used here, right. We take one of these functions, suppose log x, we take it out and take the derivative of the other function, which is x, and we take then x out and take the derivative of the first function, which is log of x. So, this was the product rule, we are applying it here. So, in the next step, what we get is log of x multiplied by d dx of x. d dx of x is by the power rule, it will just become 1. So, I am not writing that 1 here, plus x multiplied by d dx of log x. What is d dx of log x? Is it is just 1 divided by x. And so, it can be simplified a bit more, it becomes log x plus 1. So, this is the answer. All right. Second question was x plus 1 divided by x minus 1. We have to take the first derivative of this function. So, d dx of x plus 1 divided by x minus 1. So, the rule that we are using here is the quotient rule. Again, to recall, So, what we are doing here is using this rule. You have two functions u and v, both functions of x suppose, and you want to take the derivative of u divided by v, right. And the quotient rule tells us that this is 1 divided by v square multiplied by v d dx of u minus u d dx of v, all right. And that is what we are applying here. In this case, v is x minus 1 and u is x plus 1. V is the denominator, so denominator square multiplied by d dx of the numerator is x plus 1 minus the numerator x plus 1 multiplied by the derivative of the denominator, so d dx of x minus 1. And in the next stage it will become 1 divided by x minus 1 whole square multiplied by x minus 1 multiplied by d dx of x plus 1. So, again d dx of x is 1 and d dx of 1 is equal to 0. So, it becomes just 1 minus x plus 1 and d dx of x minus 1, again d dx of x is 1 and minus 0. So, it becomes 1. And here I am jumping some steps here. So, in the numerator it will be what? It will be x minus 1 minus x minus 1, right, and this is minus 2. That is what I have written here, minus 2. Minus sign is coming in the front and the denominator is x minus 1 whole square, all right. So, this is the derivative, first derivative of x plus 1 divided by x minus 1. The third problem is a little bit complicated, as you can see, as compared to the second problem. In the second problem there was no x square, but now we have x square. So, d dx of x square minus 1 divided by x square plus 1. Okay. Now, since it is a quotient that we have to take the derivative of, we apply the quotient rule once again. So, the denominator square is coming here in the denominator multiplied by the denominator x square plus 1 multiplied by the d dx of the numerator, that is d dx of x square minus 1 minus the numerator, that is x square minus 1 multiplied by d dx of the denominator is x square plus 1. Okay. The rest of the problem is just to labor through the expressions. So, 1 divided by x square plus 1 whole square, and on the numerator we are going to get x square plus 1 d dx of x square minus 1, we use the power rule and that will give me 2x, right, because d dx of 1 is 0, and minus x square minus 1 and d dx of x square plus 1, again we are going to get 2x using the power rule. In the next step we simplify it further. So, we are multiplying 2x with x square plus 1. So, 2x cube plus 2x and minus x square minus 1 is multiplied with 2x, that will give me 2x cube minus 2x. And if I simplify the numerator, I am going to get 4x, because this and this will get cancelled. So, the answer is 4x divided by x square plus 1 whole square. This is the answer. All right. We are going to attempt a lot of questions from differentiation and optimization after differentiation. So, here is another problem about differentiation. If f of p denotes the demand for a product when price per unit is p, then the total revenue function TRP is given by TRP is equal to P multiplied by FP. Find an expression for TR prime P, the derivative of the total revenue with respect to price. Okay, that is what we are supposed to do. Find TR prime P. Now, TRP is equal to P multiplied by FP. Just try to understand the economics of it. Total revenue is equal to price multiplied by the quantity demanded. How much people are buying, right? The quantity people are buying multiplied by the price per unit. So, that will give me the total amount of money that they are shelling out, and that money is going to the producers as revenue. So, we have to take the first derivative of total revenue with respect to price. So, that is what we are doing here, and instead of TR, that is total revenue function, we write it as P multiplied by FP, demand multiplied by price. And then we are using simply the product rule in the next step. Okay. We take out P here and differentiate FP with respect to P and plus FP multiplied by DP, that is the derivative of price with respect to price, and this will give me FP from the second term. We are going to get FP because this is 1 plus P multiplied by F prime P. F prime P is the derivative of the demand function with respect to price, and in the next step I take FP common. If I do so, then I am going to get FP multiplied by 1 plus P divided by FP multiplied by F prime P. So, this is the expression, therefore, this is the end result, that the derivative of the total revenue with respect to price is FP multiplied by 1 plus P F prime P divided by FP. Now, interestingly, this expression, that P F prime P divided by FP, is nothing but the price elasticity of demand. Okay. Because just think about it, P divided by FP multiplied by F prime P is equal to okay. So, this is nothing but price elasticity of demand. Okay, so this was the answer, and let me call it a day for the time being, and I shall see you in the next class. Thank you for joining.